we would love to get Meredith up on stage to talk about the Fastpath app.
Yeah, so we heard a lot about geophysics a little bit today, so I'm gonna dive into that a bit deeper now and talk about how we're using the geophysical imaging for recharge site characterization and talk a bit about the application we've developed in order to do that. So again, we're zoning in on one specific question. We've heard a lot about all the different things you need to consider with where to do recharge. I am just going to be talking about where on the ground surface are we able to find sites that can maximize the quantity and rate because of the geology of that site. So what we're looking for are these sites that have interconnected pathways through coarse-grained material from the surface down to the water table. And what we really want is a fast, reliable way to evaluate sites for this property. And we all know that this is difficult to do because there's a lot of uncertainty about what the subsurface looks like. And increasingly, people are aware that geophysics can be a really effective tool to get a more holistic picture of what the subsurface looks like and how these subsurface structures are connected. And so the two methods that we've been working with that you've already heard about today are the TTEM and the AEM systems. And so a few details about these and their resolutions and depths of investigation here. But the main thing I want to say is that these two systems are making the exact same measurement, just at different scales. And they're both really useful and valuable for recharge site evaluation. So the TTEM is really good for your site-specific local surveys, whereas the AEM is better for basin scale evaluation. And both of these data sets are going to give you measurements of electrical resistivity of the subsurface. And so clays tend to have lower resistivities, whereas sands and gravels have much higher resistivities. And this is why the method is really useful for mapping out the subsurface sediment type. But I put this up here to also remind you that resistivity is sensitive to water content and water quality. And so it's a little bit complicated sometimes to make interpretations about the sediment type with the resistivity alone. And I'll get back to that in a bit. So what do these data look like and how are we using them? Here is an example that you might have seen Aaron Fukuda put up yesterday. So this is TTEM data collected over a single almond orchard in Tulare Irrigation District. And what we're looking at is resistivity. So the warm colors are high resistivity, which we tend to associate with sands and gravels, and the cool colors are low resistivity, which we associated with our fine-grained materials. And you can see right away that at the scale of this single almond orchard, there's a huge amount of variability in what's going on in the subsurface. It looks like we've got this channel in the middle, probably a coarse-dominated channel that could be a preferential flow path for water in the subsurface. And so there might be instances where these resistivity models alone are all you need to make a decision about where you should be doing recharge. You could look at two different sites. One looks much more resistive than the other. Maybe that's all the information you need. But there are instances where you're going to be interested in these kind of intermediate resistivity values, the light blues and greens. And because of that complication in what is influencing resistivity, you've got the sediment type, you've got the water content and the water quality, it can be difficult to understand exactly what's going on in these areas. So we've developed a workflow to turn these resistivity models into models of sediment type, specifically coarse fraction, by developing site-specific transforms between resistivity and sediment type. And we do that by pairing up co-located resistivity measurements and sediment type measurements made from driller's logs or CPT logs, and building a statistical relationship between the two, which honors the physics of the measurement. Won't go into any more detail about how we do that. But once we have our transform, we can apply that to our resistivity model, and then we can get 3D sediment type models. And we can start interrogating those models and figuring out where the connected flow paths might be. So qualitatively, you could scroll through and you could find where there's a pathway. But of course, that's time intensive, and we want something a bit more quantitative than that. So we worked on developing metrics where we could take this complicated 3D model and distill it into some summary maps that could be used to support decisions. And so we have 4 what we're calling recharge metric maps that we can come up with using that model. And I'll just walk you through what each of these is showing. So the first one is our fraction coarse dominated model. Our map rather, it's just showing what's the average coarse fraction below any point on this surface. So where it's red, we've got really coarse sediments, probably good for recharge, and where it's more blue, it's more fine dominated. Next, we have path length to the water table. And this is the shortest path from any given point on the surface through the connected coarse grained material down to the water table. And so where that path is very short, it's green, the shortest path being directly vertical. And where it gets more into the white colors in this figure, that you're gonna have to take a much more circuitous route through fine dominated material in order to hit the water table. Next, we have that same metric normalized by the depth of the water table. In this case, the water table is not varying over the scale of this field, but with the AEM surveys, when you're looking at basin scale maps, that can have a big impact. You can have very variable water tables. And then our last metric is depth to the shallowest low permeability unit or the water table. And this is really builds off the need of some of our local partners where they were concerned about water ponding in the root zone of crops. Because you can imagine a clay layer that's 2 meters below the ground surface can have a much bigger impact than the exact same clay layer 10 meters below the surface. So that's the workflow that we developed for going from AEM to decision support products. And about 1.5 years ago, we found ourselves in the position where we've done this, we've published it, it's open access, anyone can do this if they can recreate our codes and figure out how to implement it, which is not very realistic. And also we saw all of the AEM data, which was about to come out of the state. We saw more and more people collecting TTEM data. So we knew that there was going to be this amazing wealth of geophysical data available, and we wanted to make sure that we were enabling people to use them using all the time and effort we invested into developing these workflows. So with that motivation, we secured some funding from the Stanford Dorr School of Sustainability, so some internal funding, and we pulled together a lot of partners throughout the state agencies, local irrigation districts, the Almond Board, consultants, and with their input and the technical expertise at Stanford, we worked on developing this application, which allows people to readily access the EM data, run it through our workflow, and create those decision support products. We also made an 8-hour course that explains how to do this, and the data explains the data that go into this, and that is as cheap as we can make it. I think it's only $50. So our app has kind of 3 main components. The first is an online database. This database contains all of the publicly available EM data in the state, so that's largely DWR's data as well as Stanford's data. And then we also enabled the ability for users to upload their own data. It'll be kept private, but you can work with your own EM data or well data if you'd like to. We have a GIS interface where you can locate all those data in the area that you're interested in. And once you select the data you want, you can launch a cloud compute session to run it through all of our research codes and create those metrics. So that's the big picture structure. And for the end of my talk, I'm going to run through a recorded demo of doing this and talk you through it. I was going to do it live, but there's no computer here. And so I'm going to be skipping a lot of detail because I can't go into all the detail now. But my goal is just for you to see how hopefully accessible we've made it. I think it's accessible and give you some motivation to go in and play around with it and use it yourself. So hopefully this will automatically start. Let's see. So when you, there we go. Okay, when you land into our GIS viewer, it looks like this. There's a couple of different layers you can choose to turn on. You can see where different boundaries are, where the EM surveys are. And you could choose to select the data you want to work with using some of those boundaries, or most simply, you could just draw a polygon around an area that you're interested in. And once you close that polygon, it's going to go ahead and ping our database or the database of data that you've uploaded, and it's going to tell you everything that's available within that area. So that includes the AEM surveys, as well as the sediment type data, which we need to build our transform, water levels, and water quality. So in this case, you can see there's 3 different EM surveys. There's a DWR one, there's a Stanford TTEM survey, and there's a Stanford AEM survey. I'm going to work with the DWR one. And you can see there's lots of sediment type logs, drillers logs. Those are mostly from DWR as well as water level and water quality. And when you're happy with the data you want to work with, you hit this start simulation button, and what's going to happen is this is going to launch a compute session on Stanford's cloud compute resources, and it's going to pull all of the data within that polygon you selected from our database and put it onto this compute session. So you don't need to download any software. This is all done in the cloud. currently for free using our resources. So there's no reason not to do it. And so once you've loaded in your data, the first page we're going to land on is our data review page. This page is mostly going to let you explore the data, and then there's one parameter you have to set, and that is the distance between the well data and the resistivity data, which we want to consider co-located. And that's important for building our rock physics transform. So this is what the review page looks like. At the top there, you can set your co-location distance. The reason we didn't set it for you is, you might have information about your site that you know better than us. There might be different optimal values for different areas. So that's kind of a knob that you get to turn. You can then use this page to just look at what the EM data look like. So here's pulling up one section. We have anything below the depth of investigation is kind of grayed out. So here you can see we've got basement rock, and then all of our sediments going off into the valley, where the blues are probably clays and the greens are probably sands and gravels. You can also visualize the wells that we have in here. So if you click on a well, it'll pop up on the other side there, where the blues are your fine grained materials, the reds are coarse grained, the nearest EM sounding is that black line, and the water table is the dashed line. And so this can there's also lots of other things you can choose to turn on and off that I'm not going to go through because we don't have an hour to do this. But look at your data, make sure it makes sense to you conceptually with what you know is going on in the area. And then once you're happy with it, you can proceed to building that transform, the site-specific transform from resistivity to sediment type. Again, I'm not going to go into any of the details of how you do this, other than to say there are different knobs you can turn, and we've intentionally left those so that you can make the decisions that are most appropriate for your sites, or you can use that as an opportunity to explore the uncertainty in the final decision products that you're creating, and help that maybe inform your decision, inform where you might want to get more data to reduce that uncertainty, etc. So we build our transform. Now what we're going to do, we're going to interpolate that EM data onto a 3D grid, and you can visualize that 3D grid. We're also going to cut out any data that has basement in it, and cut out any data below the water table, because we're just interested in from the ground surface down to the water table. And then we'll take that 3D model, we'll apply our transform, and you can also look at the 3D sediment type model. So you can choose to look at different depth slices in your 3D model. So you can see as I slice down lower and lower, a little bit on the east side there disappears. That's because we're hitting the water table there, so now it's grayed out. And we can look at different either vertical or horizontal slices, looking at profiles with depth. And we can turn on our coarse fraction model. So now the red, it's 100% coarse dominated, the blue is 100% fine dominated, and again, you can slice and dice that and look at it. This is kind of just an intermediate step. Again, let you get a feel for what the models look like. And now we can move on to our final page. This is the real kind of ta-da metrics that you're trying to create. And so now we're going to have those 4 recharge metric maps that I already explained. They're going to pop up, and you can look at those and play around with them. So this is like the longest step usually. This is real time. I didn't edit the video at all. So you can do this really quickly. Of course, there's nuances in how you set those parameters. And so you could spend all day playing with it if you want. But if you're looking at, really quickly evaluating how these AEM data or TTEM data can be used to inform recharge, I think it's a good tool. So the first map we're seeing is our average fraction course dominated down to the water table. Next, we're going to have our path length. For all of these, you have the ability to play around with the color scale to really highlight the features or the distances that are most important to you. We also have another knob to turn, and so this is the threshold that we consider sediments to be permeable versus impermeable. So that's another thing you can play with. Our normalized path length, and lastly, the depth, the shallowest no flow or water table. And then lastly, if there's a specific threshold that you think is most important or relevant to you, you can set that contour on any of these maps. You can choose to save those contours. And if you've set more than one, you can then create one final summary metric, which says that, find all the areas that agree are good for recharge based on those contours I set. So that's this final summary metric. So that's it. That's the products that you can create. If you're happy with the workflow that you've set up, you can confirm your exports, and now you're going to have the ability to download all of these products. And so we give you the option to download the 3D models. So that's the resistivity model, as well as the sediment type model. And you have a zip file that has all of those recharge metric maps. They're in a bunch of different formats, GeoTIFFs, the KML version of the GeoTIFF, so you can drag and drop them into your GIS management system of preference. We also have a file that stores all of the decisions you made, all of your inputs, so you can recreate this if you want. And then you can also choose to name your session, save it, and come back later. We will not host the final products indefinitely, so do download them if you want them, but you can at least go back and see what you did in the past. So that's it. That's our application in, I think, 7 minutes. And so please play around with it. We launched it last month. We want to hear if it works or doesn't work for you. So on our website, there's a contact, so definitely use that. We're just really, really thrilled to see the geophysics being adopted in the state. And like Stephen said earlier, we've just barely scratched the surface on how we can use all these data. So we're really hopeful that this is kind of adding one more tool in the toolbox, one more way that people can access and use these data, because we've been blown away by the statewide survey. And we're really excited to see it used in this application. And that's it.
Thank you, Meredith. That was an impressively choreographed explanation. You were on point. Well done. I hope at least many folks in here found a new tool that you're excited to go back to your office or back to your home and click around and explore and use.